Next guy is becoming quite the household name, and in as far as FIBA is concerned. He has a high profile at our seminars. He's a sponsor as well. Rich Marriage of Advanced Mechanical Engineering, a flair for the dramatic. He just arrived, just pulled in 1 second ago. He comes from a long line of engineers and grew up in the water, hence his lifelong passion for the ocean and fixing things. He founded in 1992 Advanced Maintenance Engineering, and later in 2002 Advanced Mechanical Enterprises, servicing the maritime and industrial sectors. Attended State University of New York, Maritime College, has his bachelor's degree in marine engineering, and continued his education in ocean engineering at Virginia Polytechnic and George Washington Universities. He has become, I guess you might say, a vibration specialist. So he's a guy that we've seen before, and he's going to speak to us today about noise suppression. What's that noise? Rich Marriage.
Hello, everybody. Thanks for coming, and our company is really honored to have this opportunity to be here with you and sponsor. All right, I got to figure out this. Is this the clicker? All right. Green, go. Okay, we're a local company. Hello, everyone. Again. All right, we're a local company, and we do noise and vibration services, and we try to fix the problems. Actually, that little guy in the bottom was drawn by a Dutch chief engineer from Holland America Lines. Okay, that's us in action, doing some vibration surveys. And here we are, noise suppression. All right, so everybody knows about noise and vibration. I'm sure your customers are probably on it about it all the time when they go for a ride. And how's that boat feeling? So reducing noise on board yachts has become very important, as perception and expectation of quality goes hand in hand with noise and vibration. The industry's progressed. When I first came down here, as many of you, the engines used to be mounted right to the stringers, and there were two strokes and there wasn't a lot of power there. Things have changed a lot. They're lighter, they're faster, bigger engines, and they're shaking. And if they're shaking, nobody wants to buy it. So we had to fix that. All right, so noise on yachts is described. There's two ways that we look at noise on yachts. It's airborne or structure-borne. Airborne noise is radiating from the engine components of the machinery, and it's vibrating the air molecules. And that can dissipate into the entire vessel if it's not encapsulated. Structure-borne noise is vibration energy which transmits through the hull structure. It's almost like talking through a tin cup when you're a kid. Two people talk on a tin cup, you can hear them perfectly on the end of the wire. So that vibration transmits through the vessel, and that's something we really work hard to isolate and dampen. So principal sources of interior noise, you got of course the engine room, exhaust system noise, vibration of the generator, propeller noise, reduction gear noises. Those are primary. I'm sure there's plenty more, but that's what we're going to focus on. Secondary sources of noise, noise leaking through the gaps in the engine room space, vibration from propeller shaft and struts, exhaust noise at the transom. And of course, exterior noise, you got wind noise and water wash noise. So the basics of noise treatment is, for airborne and structure-borne, is to either break the noise path, lengthen the noise path, which you do through the design stage, try to get the equipment as far away from where the people are, or you increase the attenuation, absorption along the noise path, or any combination of those three. Airborne noise is sound pressure waves moving through the air from a noise source. Sound waves travel at the speed of sound, 760 miles an hour. That's fast. Airborne noise will build up energy in an enclosed space, keep reverberating. Noise can increase up to 30% in a space with hard reflective surfaces. And in an enclosure has an opening of 10 to 15%, up to 50% of that noise will escape. So it's really important to break that sound path. Okay, attenuation. Attenuation is absorbing materials which dissipate the sound energy. This is all airborne noise treatments. Materials including carpeting, acoustic fiberglass, foam, mineral wool. And then there's noise barriers. They're like the lead, they put vinyl and they impregnate barium into the vinyl to make it heavy. That acts as a barrier to noise. And then composite materials are quite common where they combine foam, barriers, and absorbers. Sound, distance is a big thing, of course. A sound will reduce 6 decibels in intensity as you go further away. When the distance is doubled, it reduces the noise significantly. Okay, this is a sample of an airborne noise treatment, courtesy of Sound Down. It shows a bulkhead. So the quiet side's on the left, the noisy side's on the right, and it shows a film, an absorption layer, a barrier layer, and a decoupler. So what that does is it breaks the sound from transmitting through the bulkhead. Structure-borne noise, which I'm going to focus on in this presentation more than the airborne. Structure-borne noise is the #1 noise source inside a vessel. It's introduced by the machinery into the hull structure and radiates throughout the vessel. Localized hull structure resonance can amplify the vibration and noise. So sometimes you'll feel it up in a pilot house because the structure's a little lighter, and it'll get live and activate from any vibration. Vibration can be accentuated when the noise source is excited at the same natural frequency of the boat structure, and the natural frequency is the vibration at which a object wants to vibrate. It's resonance or critical. So the best way to control structure-borne noise is to isolate it, and that's where the rubber mounts and all that comes in. And damping, of course, is, I don't know if you guys have heard, they'll glue sound tiles onto the hull structure, and that'll take out the energy as well. Okay, isolators are the most effective way to reduce noise and isolate it at its source. Isolation mounts reduce structure-borne noise by breaking the path between the source and the supporting structure, and machinery should operate at frequencies 1.4 times higher than the natural frequency of the mount. The point here is that the selection of the mounts has got to be done carefully based on the weight of the equipment and the excitation frequencies. And if you're not careful, you can create a problem. On my way here, I was just dealing with one. Big sailboat wants to go to New Zealand, and they got some vibration because somebody was kind of not careful about picking out the isolation mounts. They cannot, you can actually make the vibration worse. You have to pick the right mounts. So attachment to the machinery must be all the attachments, fuel piping, exhaust systems, flexible couplings between a gear and an engine all have to be compatible with the isolation mounts. And this is the old single degree of freedom basic formula. You have a mass K is your stiffness, and C is your damping, and that's how you figure out your natural frequencies. And what's interesting about this is the heavier something is, the lower its natural frequency. So the whole object with isolation mounts is that they have a natural frequency which is lower than the machine it's trying to isolate. So what happens is the sound waves can't penetrate through because they hit the low frequency isolator, and the isolator actually moves, but very, very slowly, and it dissipates the energy as heat. So you have to do the engineering, make sure you pick out the right isolators for the right frequencies. And unfortunately, in this business, I've seen a lot of poorly selected isolators, and it causes a lot of problems. So this is just a schematic that shows like a basic close-coupled engine installation and a V-drive configuration. You can see that the isolators back aft are on the same plane as the thrust plane of the propeller shaft, which is key. If you have that isolator up high, which I've seen on some installations, it'll want to tip and pitch the whole engine on its nose, which then causes a misalignment problem, which then causes vibration, which then causes noise. And the cardan shaft down below, years ago, myself included, I thought, well, you don't need to align those things. They're flexible. You can put them any way you want. Well, it turns out a cardan shaft or a U-joint shaft has to be precision aligned. If the angles aren't equal on both knuckles, the thing will set up a vibration that's horrendous, and it actually causes both torsional and lateral vibration, and can create a lot of torsional noise in the reduction gear. So we've got a case study on that. So this is an example of an isolator. I wish I had is this a pointer? It's got this thing. Okay, there we go. Lasers. What do you know? So what this is showing here is the red one is a stiffer. This is a measurement taken on an engine at 800 RPMs. The red line, which I don't know if you guys can see it back there, but it's the big one. The red one is the excitation frequency, and this here is the frequency with a stiff mount. So this is showing the difference between how much isolation you get with a mount that's properly sized. That's where you should be, and this is where you are. So just by changing out the core element, the vibration went down significantly. Now, the question is, why don't we make all vibration mounts soft? Well, you have to pick the right mount to maintain the alignment in the position of the machine. Also, you have to consider wave action and healing and all those other good things that happen at sea. So the vibration mounts have to be, again, there's a lot of engineering that goes into these things. That's what I'm trying to get across today. Okay, so we're talking about resonance, and there's, hold on, this thing's getting ahead of me. Okay, resonance again. All this stuff about vibration boils down to resonance. And everything in nature has a frequency that it wants to vibrate at. And the idea when you're building something is to make it stiff enough or heavy enough so it doesn't vibrate. And that's the whole point with the engine mounts, is to make it stiff enough or soft enough that it doesn't transmit the vibration, but it's stiff enough to maintain the alignment. So you avoid the natural frequency. The engine RPM doesn't excite the mounts and cause them to, amplify the vibration. Okay, this is another schematic borrowed from Sound Down, my good friends over there. And it's showing an engine compartment, and there's some of the noise control features here. You have a carpet underlayment. There's your engine mounts, your barrier. A lot of times they use that plywood that has the, it's compressed with the mass stamping, so it'll deaden the noise. And of course your exhaust system. All these things have to be considered. All right, decibel. Just thought I'd talk briefly about decibels. Decibel's a unit for measuring loudness, and it's actually a ratio of sound levels. And the A scale is the one that matches our hearing closely. A quiet room is 20 to 30 decibels. A noisy engine room is 120 decibels. You start losing your hearing. An increase in 10 decibels is perceived by most people to be double in noise. It's double in sound. So it's a logarithmic. It's not a linear thing. It's 10 by 10 by 10. Noise gets. So if you make a reduction of 10 decibels, you're doing pretty well. 1 decibel is barely audible. However, 3 decibels, you can hear it. You can pick it up. And luxury comfort is 38 to 48 decibels. I mean, that's quiet. You're doing really well if you get something down around 40 decibels. There's a canned image of an engine room. It's got, you can see now these style mounts are from Detroit Diesel, and they're a donut type mount made by Lord Corporation, and there's 2 ways that mounts work. They have mounts that work in shear and mounts that work in compression. The mounts that work in shear tend to be a little better at isolating vibration. And of course, you got all your engine room insulation. Okay, anything that increases vibration will increase noise. So the better job you do at aligning it, balancing it, keeping everything tight, and making sure you don't have any bad bearings or bad gears, or misfire on the engine, the quieter the boat will be. And this is just an example. When we troubleshoot vibration, when we go out and measure it, this is an example of the kind of graphs that we get, and they show the different defects that we could potentially pick up and fix. Some characteristics of misalignment. The alignment is expressed in 3 different ways, two ways. You got your offset, your angular alignment. It's one of the reasons when you check a shaft coupled to a gear with a feeler gauge, you're not really able to see what's going on here, because you're gonna get an angle, but you're not gonna get your parallel offset, which is why our company tries to separate it and measure it with a cradle. Okay, this is an example of a cardan shaft. Hello? Somebody trying to give me a hint? All right, so this was a yacht that had really loud, high-pitched whine coming from the gear. And I was talking about these cardan shafts needing alignment. There's some noise data, and it shows these are the 2 gear frequencies, the bull gear and the input pinion. The high one's the input pinion, the low one's the bull gear. 45 teeth and 27 teeth. That gear whine is really bad. this was fighting this here. So we put new isolators under it, decoupled the noise from the hull, pin and trunnion mounts before it was hard mounted. And then these numbers came way down. As a sport fish, is there any reason why this thing's advancing on its own, or? Yeah, it's going on its own. Okay. So you have an enclosed flybridge. I'm sorry, I don't know what's going on here. It's just like... All right, well, vessel hit a submerged object in the intercoastal. Never fun. Created a lot of noise and vibration. One shaft was found with a crack in the keyway. It was partially submerged. Propellers were taken off, and none of the damage looked that bad. Propellers were taken off and fixed, and vibration was still there after that. Then, further investigation, the shaft was removed. One of the shafts had a crack in the keyway from the stress. And then the third one, we did a vibration survey, and we found yeah, see, it's missing. It's not me. Yeah, yeah, that's the next one. I don't know. Go back. I guess. I don't know. I'll back one up. I know you guys are hungry. Next one. All right, so the mounts were replaced. What the vibration survey found that the mounts were bad, and they were short-circuiting the vibration. So I guess what had happened when they had the impact is it must have caused the mount to fail, which visibly you would never see it because those mounts are encased in a steel box, and it's just not impossible to inspect them. And then both struts were found tweaked from the impact. And again, none of this was obvious. I mean, looking at the boat, everything looked fine. It was shocking. So then, pulled the shafts, and you check the alignment, and sure enough, the struts were cocked. They had twisted from the torque. And all that was corrected. So the mounts were replaced, the bearings were, realigned, and did a sea trial, and the boat ran beautiful. I got another one. This is an interesting one. Whoop. Yeah, no, it's okay. Can you go back one? All right. This is a 150-foot yacht that had high vibration. Came to us. They had high vibration. They only a week before had been in the shipyard. Had everything straightened, and everything looked good and all documented. Came back. We did a vibration survey. Found the shafts were severely bent, not like just a little, but a lot. And did a little investigation, and the engine mounts were completely collapsed, and the boat wasn't even that old, so it was kind of weird. So next one. All right, so there's the shaft and the. All right, so I'll keep going. It's all right. I don't know, it might be my presentation. Is that thing on auto advance? So we did a finite element analysis study of the shafting because we had some suspicions that there was something going on there. And sure enough, there was a critical RPM. At a certain RPM, the shaft was going into a critical, and it was bending the shaft. And the reason this thing had a shaft critical was the way the mounts were positioned on the machinery in relation to the shaft was causing the thing to flap around in a breeze. The tail wagging the dog syndrome. Yeah. So there was no easy way to fix this. The engine mounts, to reposition them in the hull would have been impossible. There was no way to move them forward, back, or change to a different style mount would have been a major, major undertaking. So a practical solution was actually to replace the shafts with a higher strength shaft material so it wouldn't bend. Seems kind of crazy, but it worked. And we changed out the mounts, and we aligned everything, and again, ran beautiful. Still is to this day. All right, last one. 100-foot yacht, chronic vibration noise. Brand new vessel. Very unusual vibration. Wasn't synchronous with the, and the reason, again, vibration and noise go hand in hand, so the thing was noisy. But the whole hull was shaking like crazy. It was just amazing, and it wasn't synchronous to either the engine or the propeller shafting or the propeller or anything. It wasn't lining up with anything. It was like a frequency that didn't make sense, and couldn't figure out what was causing it to get excited. Why was this thing vibrating? And it was at a constant, the vibration was always there no matter what speed you ran. So came to find out, after digging, the sea chest, it's a high-speed boat, and it had a big square opening for the sea chest. And found out that the sea chest was causing a vortex under the hull and exciting the entire hull structure. So a wedge was installed on the leading edge to fare the water better, and vibration went away. And frequency analysis and sea trials. Oh, sure. He was asked, good question. How do we find it? And the way we found it was we used a portable vibration meter, a FFT analyzer, and we set up vibration points all around the hull, ran sea trials at different RPMs, and recorded the vibration, and eventually we found that the highest amplitude of the vibration was right by the sea chest. Well, thank you, everybody. How did I do? Any questions? Really? The diagnostic rates, as far as
your diagnostic rates for chasing these issues. I mean, is it a time and material type of thing, or how does that work when you run into these problems?
What we've done is we've figured out that the best thing to do is just do a fixed price, and we have a fixed price when we're based here in Broward County. So if we're in the Tri-County area, what we have is a fixed price for a vibration survey. And what we've been trying to advocate is doing a survey, pre-purchase survey with a vibration, or a pre-haul out vibration survey, and then a post-haul out survey, so you can make sure that you did actually fix the problems. And we've had a good relationship with a couple of local shipyards where we've been doing pre-haul out surveys, and it's protected everybody, because boat goes away and something happens, and there's a vibration, and everybody's like, well, it wasn't there before, and we have documentation to say, sure, it was, or it wasn't.
Back over here and here, there's two.
What kind was the material of the shaft when it's bent? The bent shaft, what kind of material was?
It was a really good quality stainless steel alloy. It was. Any other questions?
Yes, right over here, Mike Reardon.
So here's the thing for the most of the people in the room, brokers anyway. And my experience with a couple of boats that have been purchased recently was that we had some sneaky expensive things after this representing the buyer. And they were cranes, davits. You know, really expensive repairs when a surveyor looked at it and said, it was okay. The world of buying a yacht and doing pre-purchase surveys, now you're advocating, and it sounds like a really good idea, that during sea trial you just included in the sea trial you do a vibration analysis, is that right?
Yeah, we can do a vibration and acoustic survey as well.
Okay. So probably something very good for the buyer more than the seller, but you know, that's the complexity of the deal. Well, and again, the buyer gets the choice of how many surveyors they're going to have on the boat, and you do it at a fixed cost.
We do it at a fixed cost, and yeah, probably better for the buyer, but also, I mean, if you have a good boat and you're confident in your boat, it can actually give it a clean bill of health, and it's good for everybody.
Yeah.
Back here. Quickly.
Yeah, I think the thing is to close is that, you know, nobody likes surprises, and you know, that's what we try to help people avoid, and we try to manage expectations and keep people happy, because happy boaters buy more boats.
Right. Question with respect to qualifying vibration of different types. Some boats, I would imagine, I'm right here. Can you see?
Stand up, Jeff.
There you
Stand up,
go.
Jeff.
I mean, some boats are going to have inherent vibration because they're you know, a Fed ship is obviously going to have less vibration than, say, an azimuth or you know, a less expensive build. In some cases, when you do these surveys, or do you say, well, this is just inherent in this type of build, you're going to have this type of vibration, or does it always come down to some sort of deficiency that needs to be corrected?
No, it's a good point. Not all boats are built the same, and there's a market for every boat. And we are, you know, I've been in business, I've been doing this for close to 25 years. So we've accumulated a very vast database of different types of vessels, and we know when a vessel runs well and when a vessel has it, you know, and one of the things that, and we're not perfect. Sometimes we run into an issue where it's because of design and engineering that frequencies will line up. For example, if you have a 2-to-1 gear ratio, the vibrations from an engine misfire and a shaft being bent are actually going to turn out to be at the same frequency, and it gets a little tricky in trying to troubleshoot those kind of problems.
I mean, how often have you opened up a can of worms or pointed to some type of vibration that couldn't be resolved or clearly identified?
I could count on one hand the times that that's happened. It's happened. I would not deny that it's happened, but usually we persevere, and it doesn't turn into a huge, unending can of worms. It's usually, what can happen is if you're not taking a scientific approach. I've seen it go both ways, where if you don't take a scientific approach to trying to investigate a problem, a vibration problem, and you just, well, we think it's the propeller. Okay, change. We think it's this, we think it's that. And before you know it, you're in deep, and you're nowhere further along. And it might be something really simple. So most of the time, I'd say that it's never happened where we've not been able to completely identify a problem, and it usually is not that painful.
Thank you.
We have a question right over here.
Is your technology able to detect underwater exhaust vibrations that are caused by underwater exhaust? And are you able to remedy those problems?
Exhaust gas frequencies are a function of the engine firing frequencies. What we do is we actually measure on the exhaust system itself. We take readings on the exhaust system and where it discharges from the hull. And then, you can't just, vibration is a tool. It's not something you can use exclusively by itself. It's like when you go to a doctor for an EKG, for a checkup. He's asking you about your health. He's asking, hey, have you had a grounding? He's checking more than just the vibration. You're looking at the whole picture. And with exhaust systems, I was on a boat recently, and our company had found significant problems with the running gear and repaired it. And we went on a sea trial, and the captain was complaining, they're still feeling this vibration in the pilot house. And I'm like, so somebody else had worked on the exhaust system. I went down there and looked at the exhaust, and sure enough, all the isolators from the exhaust were free, not carrying any weight. And literally, while we were at the dock, the boat was in idle, not even underway, and the engineer adjusted the isolators on the exhaust hangers while we were sitting there, and you could feel the vibration go away on your feet. So, yes.
Sometimes it's the simple things, I think is what you're saying. Any other questions here? You'll need to repeat this, Rick.
Yeah, isolate is a motor mount. And there's many manufacturers. Usually the rubber compounds they have very good natural frequency characteristics. And there's companies that combine rubber with steel springs. One of the things that, it gets a bit tricky when you're dealing with thrust force. And you have to have the right combination of mounts to be able to absorb the thrust. A 150-foot yacht will produce 30,000 pounds of thrust. So you got to really make sure you're set up for that.
Any other questions? These are good questions. I think everybody's encountered vibrations at one time or another, that's why.